Hey there, in this recording I'm going to talk about Minkowski and what's called the invariance of the interval, and I'm going to relate the Minkowski work to PySpace, and I'm going to talk about the hyperbola, and I'm going to explain the formulas and show how they relate to Pi-Shells, which are atoms that can shrink due to movement. The Minkowski work is just another way to look at Pi-Shells. So he formulated the interval here as the s squared, the distance, and he would square the x and the y and the z, and he would subtract c times t, which is the distance, and that would give you the interval. And he showed that this was a special form of the Pythagorean theorem. If you've read any of the other PySpace documentation, I've shown that the Lorentz transformation is essentially just area loss of a sphere. So the formulation that Minkowski came up with was that for all observers, this holds true, which is you start with vt squared minus ct squared, and for all observers, this value here, it always ends up being 0. Now, the way you interpret that in PySpace is these are areas. So the area of any observer sphere when it loses all its area is 0. So that's the interval, right? So let me just draw this to make it a little bit clearer. So what we have is a stationary Pi-Shell here, the yellow one, traveling at the speed of light, which is a subtraction of area. So this minus the subtraction of this area gives you an interval of 0. So that's what the 0 interval means. It means it's traveling at the speed of light, and when a Pi-Shell or an atom goes to the speed of light, in this theory it has no more area, so it turns to a waveform, which is defined by E is equal to HF. And in the Minkowski way of seeing it, that just means the interval is 0. Okay. You always square things in the Minkowski work, and the reason why you square it according to the PySpace theory is that we're dealing with the area of a sphere. The hidden variable here is pi, so it's pi times c squared, which is pi d squared, which is the diameter, which is the total area of the object. Therefore, the interval is 0. So it doesn't matter how big or how small your observer atom is. If you travel at the speed of light, well, all that really means is you're losing all the area of the sphere, and you've returned to a kind of waveform. So that's the way you describe it in PySpace. Now, what we're going to do next is relate the space-time diagrams that Minkowski came up with to this concept of Pi-Shells. Once again, a Pi-Shell is just a single atom or a group of atoms making up some kind of larger sphere. Could be a large object, or it could be a planet. The point is it's spherical. Okay. So I move down to the Minkowski formulation, which is here, which is the interval. Again, this is just the difference in the area loss. So this is the observer sphere minus the amount of the total loss of area, and you get the interval. So one of the ways people learn special relativity is they have these things called space-time diagrams, and in the you have the x-axis and you have the time t-axis over here, and time is regarded in these diagrams as another dimension. In the PySpace theory, which is just a theory of spheres, time is a attribute of the atom. Each atom has its own clock tick, if an atom is smaller, the clock tick is slower, and if an atom is larger, it's relatively faster. But if you're in a room full of atoms of a certain size, time will run at at a constant rate for you, and I have another. Uh, so so time will run at a particular a rate if it's smaller. Um, Now, if we look at these diagrams here, uh, basically this is the starting point here, and the cones, as they're called, spread out in either direction, and this is the future, and this is the past. So how do we relate this to the pi space theory? So this is an object moving. These lines here represent the speed of light. This is the maximum speed at which an object can travel at. So in here, the velocity is greater than 0 and less than speed of light c. Therefore, the pi shell is not fully compressed relative to the observer. All that really means is that the pi shell is completely compressed along here. It's traveling at the speed of light. Outside here, it's called space-like. In other words, there's no the pi shell or atom doesn't really exist in this place, because it's faster than the speed of light. So the pi shells exist inside these cones here. This is the past, and that's the future. So the Minkowski interpreted those intervals in 3 ways. He said if they're less than 0, they're time-like; if they're 0, they're null; and if they're greater than 0, they're space-like. So if we translate that into the theory of spheres, pi space, in the interval less than 0 is time-like. This means that the pi shell is traveling at less than the speed of light, and it's not completely compressed. If the interval is 0, what's called light-like, this means the pi shell is traveling at the speed of light and is completely compressed. It has lost all its area. If the interval is greater than 0, it's space-like, and it's not possible for a pi shell to travel at this speed. It refers to positions outside the diagonal line. So that's how you can if you know the special relativity diagrams really well. That's how you relate them to the atoms. Now, obviously, traditional special relativity has clocks, rods, and whirl lines, and they all change depending on the amount of velocity. So they're all built into the sphere. But Minkowski came up with what was called the invariant hyperbole. So he expressed this idea as t squared plus x squared minus t squared plus x squared is equal to a squared. So what he did was he showed that the values that come out are non-linear, and he called this a hyperbola. So the reason that we have a hyperbola, the squaring function here, is because we're dealing with area change. So again, we go back to the idea that a sphere has an area which is defined by pi times its diameter squared. The maximum diameter is the speed of light, so it's pi times c squared. So what you will see is that as objects travel at higher velocities, the values are based on the squaring of the values, and they're not linear. Even though in gravity at lower rates it's quite linear, when you move faster it's not linear. So in pi space, I have come up with I've modeled that in the advanced formulas, but just for the purposes of this this diagram, this is just trying to tell you that the area loss is non-linear, and it's the area loss of a sphere, and all that an atom is in this theory is a sphere. So that's the way to understand the Minkowski work in terms of pi space. Inside here are the pi shells losing area as they move out and up, yeah, and from this point here, and in the past losing area as well. and at the edges they're no longer spheres. They've lost all their area along these lines, and they behave more like waves, which in the Minkowski work is called light-like. And that's it. That's how you map pi shells and pi space to the Minkowski work. If you're very familiar with the Minkowski work, and you just wonder how do I explain that in this theory. Thanks.